So just a reminder that we I'm gonna hand you guys the exam on Friday, and then it'll be due back on Monday. Okay. So I'm just going to continue with rational canonical form now. Okay. So last time I guess we did some p-adic stuff because you guys wanted to see that. But the time before that, I gave you kind of the fundamental theorem of modules over PIDs. So recall that we had this fundamental theorem which would said that if R is a PID and M is a finitely generated R module, that's an R. Then M is isomorphic to R mod A1 direct sum R mod A2 direct sum R mod A. I don't know what letter we want to pick here. M maybe. Direct sum R to the R. Okay, and so these things here, these were called the invariant factors. Either the polynomial or either the element itself or the whole submodule. So there's kind of an abusive thing where we talk about both of them. And they satisfy a divisibility condition that condition being A1 divides A2 divides ... divides AM. Okay, and then this thing here, this R here is called the rank of the module. Okay, so I used a little bit different notation every time, but it's the same idea that you have a direct sum into cyclic modules, and then they have a certain annihilator. Okay. All right. So today, rational canonical form is about specializing this discussion to this linear operator. So rational canonical forms are about specializing this discussion to f of x modules for t associated to linear transformations t from V to V on finite dimensional F vector spaces. F vector spaces. Okay, so here F is a field. All right, and the field can be really of any characteristic. We can do all sorts of fields. Okay. All right. So that being said, I need to talk a little bit, give you some preliminaries, some like linear algebra preliminaries to kind of start this discussion. Okay. So, all right. So let's just start. So so let T from V to V be a linear transformation on an F vector space, a finite dimensional F vector space. Let me turn this off, sorry. On a, let's say, finite dimensional F vector space V. Okay, so I'm going to do just kind of like so you guys have probably seen this before. I'm going to do it again. It's just eigenvectors, eigenvalues, eigenspaces, and then characteristic polynomials. Okay, so so definition. So an eigenvector for V, so sorry, for the linear transformation T, for T, is some non-zero, that's important, V in V, such that, well, TV is equal to lambda V for some lambda in the field. Okay, that's what an eigenvector is. So it's when you apply the linear transformation, you get a multiple of your thing out. This thing here, this scalar here, this element of F, is called the eigenvector. Or sorry, eigenvalue. Sorry. Is called the eigenvalue. And so, and I just want to make some remarks here. So note that, so eigenvectors are not zero. Eigenvectors can never be zero. Okay, eigenvalues can be zero. All right. All right. So, all right. So, what else are we going to have? So, definition. So, so given some lambda in F, so the eigenspace for associated to lambda, sorry, is this is the subspace V lambda. This is the set of V and V such that TV is lambda V. Okay, so this is what the eigenspace is. Okay. So this thing, it just contains all the eigenvectors and zero vectors. Okay, so you guys know all this. So eigenspaces and eigenvalues, they're usually helpful over algebraically closed fields. Okay, and we're going to be doing things that work over the rationals. Okay, but let's get into that. Okay.
Taylor, can I ask a question quick? This is a clarifying thing, and my rusty linear algebra. If eigenvalues can be zero, that implies that the null space, or like the kernel of this transformation, is an eigenspace.
Yes.
Okay, I just wanted to make sure I wasn't totally losing my mind.
Yeah.
Cool. All right.
The kernel is a eigenspace, according to this convention. Okay. So, all right. It freaks me out every time. Let me tell you. Okay, I freak out about. So that's probably the main thing I freak out about with eigenvectors and eigenvalues. Before I go do this every time, is like, do we want to allow 0 or not, right? And I check the book, and they say you should allow 0, so I'll allow 0.
Okay, cool. Yeah, it like made me feel weird, so I wanted to ask.
It makes me feel weird.
Okay.
Yeah.
Glad I'm not alone. All right.
Okay. Yeah. Okay. Maybe I'm we'll see. We're gonna find out what happens. Okay. So, all right. So so the characteristic polynomial. I mean, whenever you feel, in general, right? Whenever you feel weird about something, like, you just kind of like wait to see what happens. So if you don't like a hypothesis, right, or you want to introduce a hypothesis, try it and then see what happens. And then whatever happens is, you're going to be forced into doing something, right? And so it doesn't really matter how we define it right now, because I mean, it does in the sense that, like, we're going to use it later, but once we start using it, that's when we're going to really see why it matters and why it doesn't matter. Okay. So the characteristic polynomial of t, right? So is this following polynomial is the determinant of x minus I minus t. Okay, so t is the linear transformation, and so we're going to denote this by pt of x, and this is a polynomial in f of x. Okay, so in general, okay, so here, so let me just say that, let's make some observations here. Okay, so to take a determinant, the way that you guys know how to do it now is you make a basis, right? And then you take the matrix in that basis, or the linear transformation in that basis. So this is independent of the choice of basis. For t. Okay, so let's do it. So let A be a matrix for t in one basis. Okay, so let B be a matrix for t in another basis. Okay, so this means that, well, actually, let's do it this, do I want to do this? So this means that B looks like P inverse for some change of basis matrix of basis matrix P. So this means that i.e. P is an element of GLNF. So this is invertible matrices. I just want to remind you that this is the general linear group. This is invertible matrices with coefficients in F. Okay. So GL, maybe I should say, so N here is the dimension. So here, this N is the dimension of V. Okay. So, all right. And so now let's take the determinant. So the determinant of X identity minus A. So this is the same thing as the determinant of, let's do B. Okay, so this is the determinant of X identity minus P inverse. This is the determinant of X times, okay, so we do P inverse. minus PAP inverse. So x is a scalar, so you can just move it out. So this is the determinant. Okay, so this is P x minus A P inverse. Okay, and now we know that, so I guess this is x times the identity if we want. Okay, so sometimes we just omit the identity when we're multiplying by a scalar. Okay, so this is the determinant of P times the determinant of I x minus A, and this is the determinant of P inverse. Okay, so the determinant is actually a group homomorphism from this group into, so note that the determinant here from GLN F to F star is a group homomorphism. Okay, so these two things cancel. Right, and then you just get that this is the determinant of the identity of x minus A. So these two things are the same. Okay. All right. So all right. So the other thing that I wanted to note is that in general, you know, the determinant, the characteristic polynomial, PT of x, does not split into linear factors. So, for example, if you have something in rational coefficients, you can have a polynomial that you know doesn't contain all the the field may not contain all the eigenvalues over the algebraic closure of the field, right? And so it won't. Unlike in like your ODE class or something, it's not going to always factor over. It's not always going to factor over the complex numbers. Okay. Okay. So if F is algebraically closed, then it will. Okay. All right. Okay, and so now there's a big theorem that I want to say. So there's this Kaylee-Hamilton theorem. I think I might have already stated this once. Did I state this once already?
I don't think so. I'm not sure.
So it just says that so let T be a matrix. So let T be a linear operator. On a finite dimensional vector space. Okay, so it says that PT of T is 0. Okay, so so this is saying that any linear operator is killed by its own characteristic polynomial. Okay. So we're going to prove this later. Maybe I should do this here, and then. So we're going to prove this later when we do Nakayama's level. So a proof. Okay, so I'm not going to do this now. I'm going to do it later. All right. So all right. So this is one of the things that annihilates a matrix. Okay. So there's also this thing called the minimal polynomial. Okay. So let t from v to v be a linear operator on a finite dimensional let's say F vector space V. Okay, so the minimal polynomial is the smallest thing that annihilates T. So the minimal polynomial of T is the unique smallest so it's the unique smallest polynomial. Let's say the unique. Let me say this. It's the unique monic. So monic means that its top coefficient is constant, such that the annihilator. Okay, so this is V viewed as an f of x module via T. Okay, so this thing is generated by the minimal polynomial. Okay. Okay. So another way to say this is that so let me make another remark. So there's a ring homomorphism. Yeah, did you want to say something?
I was gonna say, isn't that kind of another way to say that it divides it to the minimal polynomial divides anything that annihilates?
The minimal polynomial, for example, will divide the characteristic. So since this one annihilates T, the minimal polynomial divides the characteristic polynomial, right? So that's one thing that we will know. So, but let me just give you another perspective on this. So there's a ring homomorphism, right, from f of x to say like f of t. So this is just like all combinations, polynomial combinations of t, and this is maybe the evaluation at t map. This is given by x maps to t. So this is but in the f just goes to f, right? And it's linear on f. Okay, so it's uniquely determined by this property. Then
that's the one we're doing like t cubed means to transform the vector three times or whatever composition.
Yeah, exactly. X cubed would map to t cubed in this map. Exactly. You know, an x cubed plus x plus 1 maps to t cubed plus t plus 1. So we're using the fact that you can add linear operations on a vector space. Okay. So this is the ring. You can also view this as a ring here. And then the kernel of this map is M is this minimal polynomial. Okay, this is the same thing for like if so note that this is for say alpha an element of f bar, the algebraic closure of f. So last semester you guys talked about minimal polynomials associated to algebraic elements, right? You know, the evaluation, the kernel of the evaluation at alpha map. So here, evaluation of alpha is this map from f of x to f bar, given by this variable x going to alpha, right? then this thing here is m alpha of x. So this is the minimal polynomial of alpha. So this is kind of an analogous situation. Okay. All right. So you have this minimal polynomial, and so note that the Kaylee-Hamilton. So note that by the Kaylee-Hamilton theorem, P of t, pt of x. So this is in the kernel of the evaluation at t map, right? So this implies that P of t of x is an element of mt of x, and this implies that mt of x divides pt of x. So this is like the first bit of information that we have about the minimal polynomial.
Could I see the annihilator definition again?
Yeah. So the annihilator definition is here.
Because then that's an element of the f then, right? Or the annihilator.
Yeah, this is still an ideal. Yeah.
In f
so
of
the
x,
annihilator here, this is everything that annihilates the VT, this vector space, right? As a polynomial combination of t. So these two things are really the same. So what is this thing anyway? So this thing this is the operators. So this ring here is just a ring of operators on V built from T.
They're all linear transformations right?
They're all linear transformations, yeah. These are all linear transformations here, right? It just happens that you can compose these linear transformations. Right?
Is that why you're using the name operator also then, or?
Yeah. Yeah, you can compose. I don't know. I'm just calling them linear operator, linear map, linear morphism, same thing. Yeah.
Okay. Yeah.
I'm just saying. I don't know why I'm using operator is just a word I use for linear morphism. Yeah. 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 So this is the same thing. So these two things are really the same. Same. As Davey would say, same. Okay. So yeah. So what all I wanted to say about this is that this is the first piece of information important piece of information about mt of x. Okay, so all right, so let's see what else I have to say about this. So there's all right, so okay, so one thing that we did do before is we did do okay. So so yeah, so this is what I wanted to do anyway. Okay, so let's look at what happens to. Okay, so what does the minimal polynomial have to do with invariant factors?
Maybe this is where you're going, but did you mention that the characteristic polynomial is the product of the invariant factors?
The characteristic polynomial is the product of that is true. The characteristic polynomial is the product of the invariant factors. I have not said that yet.
Okay. I didn't.
Yeah. So yeah. So let me just say that. So spoiler. Well, let me write this out. So now the fundamental theorem to V of t. Okay, and we'll get that V of t looks like, okay, so it's finite dimensional, right? So there's going to be no free part, right? So this thing looks like f of x minus a1 of x. Direct sum, okay. F of x mod okay, so I did am before, but I also have this m. Is it okay if I use m twice?
Sure.
Okay. Just this subscript n has nothing to do with that m.
Yeah, once it's counting.
Okay, so there's no torsion part here, so there's no free part. There's no free part. Since v of t is finite dimensional. Okay, so one thing that you can see is that the degree, right? So we know that this module is going to be like this. So the degree of a1 of x plus the degree. Okay, so the degree of this is the dimension of this part, right? So let me just remind you that.
This is terrible. What was v sub t again? I'm sorry.
V sub t is v. Is v. This is v viewed as an f of x module via t, right? So it's like this weird module structure that I give to v via the linear operator t. Okay.
Once you fix a t, you've got an fx module.
Yeah, once I fix the t, you get an f of x module. Yeah,
you
that's
don't
right.
really have that until you do that, then, right?
Yeah,
v
you don't really
is
have
an
that until you do that. Yeah.
Okay.
That's why I put the t there, because the module structure depends on t. Right? If I were to switch the linear operation t, then the vector space would become a different module under, with it would give it a different f of x module structure.
Okay.
Like q to the n has many different module structures that you can give it depending on the linear map that you're working with.
So this gives us a way to kind of characterize linear transformations on v, then, in a way.
Exactly. That's exactly what it does. It gives us a way to it's a way to study linear transformations on v by kind of viewing it as a f of x module in this way, and using the fact that we know what f of x modules look like. Yeah. In particular, right, so one of the things that we have is that, okay, so what I wanted to remind you is, so this is the dimension as an f vector space of f of x mod ai of x. So this is the degree of ai of x as a polynomial, right? So this is the dimension as an f vector space. Okay, this is the degree, and so this tells us that the dimension of v is just the sum of the degrees.
And that's just like it was last semester also, where if you've got a polynomial, minimal polynomial that's like x squared minus 2, then the splitting field or whatever has degree 2 extension kind of thing.
Well, not the splitting field, but well, I guess in that case, if it's degree 2, then it will be. But yeah, so just when you mod out by a polynomial, the dimension of the vector space is the degree of the polynomial.
Okay, yeah.
Exactly. Yeah, it's the same thing, right? So we have that this is true. So we also have this condition that all of them divide each other, right? So this is what you were saying, that so the condition was that a1, this thing divides a2 of x, divides divides am of x. Okay, so we had this divisibility condition on the invariant factors. So, and notice that the annihilator of, okay, so the other thing is that also the annihilator of f of x of these modules well, this is just ai of x. It's written right there, right? It's written right there, right? So so this is what the annihilator is, okay? And so all of these things divide am of x, right? And so am of x will annihilate everything, right? So since all of these guys, since all the AIs x's divide am of x, and am of x is the annihilator of the last one, of the last invariant factor. So now I'm really using this abusive thing. I'm talking, in this sentence, I'm talking about the invariant factor as one of the direct summands rather than, and in this sentence, oh, and then in this sentence here, I'm talking about the invariant factors as a polynomial. Right? This is where I'm using it as a polynomial, and in this sentence, I'm using it as a direct summand. Right?
Okay. I just verify on the annihilator statement there. So in the annihilator is things from f of x. So if you're a polynomial that annihilates something from our new vector space, then you are divisible by a sub I, basically. So like if you're a polynomial that annihilates something from, yeah, that vector. We have, because that's a vector space. F of x mod a sub I, that's a vector space, right?
Yeah, it's a vector space and it's an f of x module.
Excuse me, is it a field? Is actually what I meant to say. It's not a field.
Right? It can't be. It's not a field. It's not a ring. We're not viewing it as a ring. We're viewing it as a cyclic module. It does. Okay, so it is in bijection with a ring, but we don't view this one as a ring. And this is what I was talking about before. It's like we have to have our module glasses on, right? And this is like, right. View this as a module, not a ring.
Yeah, right. That and modules are the ones that have annihilators anyway, so that makes sense. Right?
Yeah. Rings do have annihilators because rings are also modules, but yeah. So this tells us that the annihilator of this whole thing, right, is sorry, of v of t. So this is am of x. So, you know, am of x and mt of x are associates. You know, and if we force ai of x to be, if we force ai of x to be a monic, then, you know, the ai of x to be monic, then am of x is mt of x. Okay, so the last invariant factor is the minimal polynomial. And then you have a bunch of things that divide the minimal polynomial before that. Okay? Also, okay, so now in this thing, okay, so that's what we have. So the last invariant factor is the minimal polynomial. There's this other piece of information here, right? So the sum of the degrees is the dimension. Well, also, you know, this characteristic polynomial, that's also degree equal to the dimension, right? So that suggests, right? So there's this theorem that Rick was saying, right? That a1 of x, a2 of x, am of x is equal to the determinant of xi minus t. This is the characteristic polynomial. So the product of the invariant factors, is the characteristic polynomial.
You were calling, is that the one you were calling P sub t also? Or was that something else?
P sub t.
Okay.
Yeah. So all right. So how could we get this? Right. So what's happened here is that, like, there's a certain choice of basis, right? So if we choose, so the fact that we have this theorem here, this big theorem in red, I'm going to circle it in red, right? There's a there's a bunch of subspaces. So this is a subspace. This is a subspace. So there's a choice of basis. So there is a choice of basis. Basis here. So that on each of the subspace, right, T acts by multiplication by X bar. So that on the subspace, corresponding to AI of X, T acts like multiplication by X bar on this space. Okay, so this is just like f of X bar. Okay, so and really that T in this choice of basis where we get this isomorphism, right? So T is really a block diagonal matrix, right? So T, this means that T here is this big block diagonal thing. Okay, so this is a big block diagonal matrix. And do you guys remember what these matrices were called? Maybe let me put them as A's right now. So we took a little aside to do something here at the very beginning, a long time ago.
That wasn't the Smith, right? No. That was...
No. It was older than that. It was. How long ago did we do this? So this is where we started this. Where's the companion matrices? Did we even do it before this?
Yeah, I remember we did that. By norms.
Yeah. Okay. So it's even. Here we go. Norms. There we go. Companion matrices. Oh, let's go back. Dang it. Here we go. Right? Remember this thing? So we had this, we looked at this ring here. And then we looked at what multiplication by X did on a ring, or on this, well, this module, right? So now if we look at multiplication by X here, well, that's a linear transformation as an F vector space, right? It looks like this.
I didn't quite understand. I've seen that before, that acting by left multiplication. Is that because, like, if you take, is that under composition, that the left multiplication? So like T times T squared is T cubed. I'm not sure.
That's true. T times T squared is T cubed.
True. Okay.
So all I'm saying is that, like, the map T, right? So like so the theorem says that V breaks up into a direct sum of certain subspaces, right? And those subspaces, right, look like these quotient rings here, right? They look like these vector spaces. And they're such that T acts on these subspaces as multiplication by X bar. Okay? And we know what multiplication by X bar looks like. It's this. It's this companion matrix.
Yeah, it just moves one basis down.
Yeah, exactly. Moves one basis down and the whole thing. So if we go back to our thing, right? These are all companion matrices. This is the companion matrix of A1 of X. This is the companion matrix of A2 of X. This is the companion matrix of AM of X. So this is what T looks like. T looks like this. And it's in block diagonal form, right? And this thing, this form, this is called, this form here is called the rational canonical form, right? So the matrix after a change of basis, so this is the rational canonical. Form of the linear transformation T. These are the companion matrices. So this is block diagonal. Right? And the blocks are companion matrices. Okay? And this whole thing about this isomorphism here, so this isomorphism here, right? So this is saying that there's a choice of basis, right? So that it looks like this. So this is this isomorphism. There's this isomorphism. Okay? So the isomorphism says, so what a corollary is that, so every matrix A in M and F is similar to a unique matrix, a unique Jordan canonical form. Or not Jordan, sorry, rational canonical form. I.e. that there is, you know, P inverse. So there, so that means that there exists some P in GLNF such that this thing is equal to, this is equal to R. And so this thing looks like, you know, C of A1 of X, C of AM of X. Okay, the other corollary we get is, so we also get this thing. This thing proves this thing. Right? Why? And why is this? So the proof of this. So it proves this because the determinant of block matrices is the determinant of the blocks. So the determinant of block matrices is the product, oh, I'm over time, of determinants of blocks. And let me just say one last thing. And here, the determinant of each of these companion matrices, as you look back in the other part, in the last part, right? The determinant of those companion matrices is the polynomial associated. So the determinant of a companion matrix of a polynomial f is the polynomial f. And so since we have this with a bunch of invariant factors, that shows us that the determinant is a product of those invariant factors. Okay, so I'm going to stop the video and let you guys ask questions after I stop.